Okay, good afternoon, everyone. How come the class is so small today?
Yeah, that's what I am also surprised. It's a
Maybe I
we are
made
held.
some. I made a comment in that talk, VG talk, that
Yeah,
we'll
yeah,
not
yeah,
be
yeah,
having class today, something like that, right?
yeah. But only there were only not only 20. There were total 25
They
students.
must have told others. No, okay, fine. People are
Yeah,
coming.
yeah,
Let's
yeah,
go ahead.
yeah.
Okay, so until last class we discussed the discrete Hopfield network. Now let us look at an extension of that called the continuous Hopfield network. So then we'll look at a further extension of continuous Hopfield network with which we'll be able to make a contact with hippocampus, a part of the brain which has important roles in memory storage and retrieval. So we have seen that in the discrete model you have a vector. The state of the network is a vector V, where each Vi, right, is sorry. So each Vi is plus or minus one. Whereas in the continuous model, each Vi, so this is a discrete, Vi is plus or minus one. In the continuous model, Vi is in the open set minus one and one. It can take any continuous value between minus one and one. And second thing is, in the discrete model, you have, so discrete model, discrete Hopfield neural network. You have the inputs, right? You combine all the inputs, pass it through a signal function, and you get the output Vi. These are the weights, Wij. This is, let's say, Vg. In the continuous model, you have exactly the same kind of inputs, and you sum all the inputs. Okay, and then you have Wij, and there's an internal variable called Ui, and then as a function of that, you calculate the output Vi. So this is a static. There's no such internal variable here in the discrete case, and here it is related by a static function. So Vi at t plus one is a function of, let's say, g, the step function, sigma Wij Vj at t. J goes from 1 to n. In this case, it's not a static function, but it's a differential equation. What is the differential equation? Let's see that. It is given by this. So this, if I have a neuron, this is inputs from any other neurons. The internal variable of this is Ui, which is given as a function of the external inputs by this differential equation like this. So du by dt is Ui by dt is equal to minus Ui plus sigma Wij Vj plus Ii. So Ii is like the external input. Let's say each neuron, right, in addition to getting inputs from other neurons, you think it also gets inputs from the external world. That is Ii. Now, given Ui, Vi is simply calculated by applying the signum function. So in this case, instead of using the sine functions, we need derivatives here. We use a smooth version of the sine function, right? This is the sine function or signum function. A smooth version of that is the tanh function, which looks like this. So we use tanh function. So Vi is equal to tan h of lambda Ui. So that is here in the function g. So generally lambda is considered to be like a large positive number, either greater than 1 or greater than 1. So that the tanh will be has a sharp transition at the origin and it kind of approximate the signum function. Now you can easily see how this can be related to the previous discrete model. Because take the case when Ui goes to a steady state, right? It goes to some fixed point and stays there. So then at steady state, steady state, Ui dot is 0. So at Ui dot is 0, here you have minus Ui, so that is Ui is equal to sigma Wij Vj plus Ii. J goes to 1 to n. right? And at that point, so Vj is given by tan h of this, so g of ui. So Vj is equal to g of ui, uh, which is equal to g of sigma wij, etc., etc., etc. So Vj is equal to sigma wij. So that is pretty much like this, right? At steady state, since Vt plus 1 is equal to Vt, you'll have same vector on left and right sides. That's the equation you will have at steady state in case of discrete Hopfield network. You have almost identical equation in case of continuous Hopfield network. Only thing is, instead of signum function here, I have the tan h function here, but I'll make the tan h function have high slope at the origin by increasing lambda. So the two equations, so at steady state, both the models point to the same solution. So therefore, you can draw parallels between the two models, right? What the discrete Hopfield network approaches, the solution that approaches through discrete steps or jumps, the continuous Hopfield network approaches by smooth evolution in the state space. So that is one important difference. And just as discrete version has this energy function, which goes down right at every step, right? The continuous version also has an energy function, which goes down as a network evolves. So this kind of a function is called Lyapunov function in dynamical systems theory. This kind of function is generally proposed to prove that certain dynamics is stable, because when you have a function like this, which is bounded and which goes down monotonically as the system evolves, then obviously it has to reach a stable state at some point or other, because some function is reducing monotonically. So you can show that the system, whatever dynamics you are proposing, is stable. In the context of dynamical systems, it's called a Lyapunov function. But since the Hopfield's original motivation is to compare the dynamics with the spin glass dynamics of the magnetic materials, where the same expression is Hamiltonian or the potential function, so you call this energy function. Okay, but whatever is terminology, this is the function. So it has three parts. The original discrete Hopfield network had only one part, the minor half sigma sigma wij vi vj. In addition, you also have this extra term where this you calculate an integral over g inverse. The g is the tan h function. You know this inverse of that, right? Inverse of g inverse of v, integral over dv. And then something that we didn't have in the original discrete Hopfield network, which is the external input, and we have that. There's another term correspond to that. So this whole complicated expression, right? This will go down monotonically with time, and after some time it will converge. And saturate. I mean, it doesn't change anymore. So how do you show that? Basically, we need to show that dE by dt is less than or equal to 0. That's how you show that E monotonically decreases. So if you differentiate this with respect to time, you get this expression, right? Sigma I equal to 1 to n. But this has double summation, so the second summation goes into the brackets, and you will get wij vj, and you will have, you're differentiating this with time, so you'll have so since it has quadratic terms, products of vi and vj, you differentiate with respect to time, you get something like, we get one term where you have dvi by dt times vj, and you will have other term where you have vi times dvj by dt. But since wij is equal to wji, you make use of that symmetry, and you get this simplified form. You get this internal summation goes inside, you have wij vj times outside you have dvi by dt. The second expression for differentiate, so v is equal to g of u, so therefore g inverse of v is equal to u, so this is u. So therefore derivative of this is simply, then you have integral of that. So derivative of that is simply g inverse v, which is u. So you have minus u here, because minus sign has come out here. And then this is nothing, you just have ii will come out, and dvi by dt will also come out here. So now you see that this expression inside the brackets is nothing but your dui by dt. So you use that here, and you get sigma over I from 1 to n. dui by dt times dvi by dt. And note that again, if you invoke v equal to g of u, so dvi by dt is equal to g prime of ui times dui by dt. So dvi by dt is equal to this. So you get this, and that means you have g prime times dui by dt whole square. Now g prime, if this is a sigmoid function, its derivative is always positive because it's a monotonic function. It looks something like this. So g prime is also positive, and there's a minus sign in the front. So on the whole, you can say that the expression is strictly negative or equal to zero. It will become equal to zero when dui by dt goes to zero at stable when it goes to stable state. So this actually proof of convergence is easier in this case than in the case of discrete and Hopfield network. Now, if you look at a single Hopfield network, it can be written like this because if I remove all the cross connections that you get from other neurons, right, and I just take the ith term itself, it looks something like this. And if I also ignore the external input, it looks something like this. And if I, for even simplicity, if I with this lambda, for simplicity, if I take w equal to 1, so that the self-feedback term is 1, then I get du by dt is equal to minus u plus tan h of lambda u. So this is the dynamics of a single Hopfield neuron. We actually looked at this neuron model way back when we were discussing simplified neuron models. So here you can see that so I want to understand the zeros of this, understand stability. How many stable states does it have? So we can plot this as, I want to know when this expression on the right side becomes zero, right? So for that, what we will do is I take two expressions. One is y equal to u, another is y equal to w tan h lambda u. And I'll see when these two curves intersect. That's when, because if you take u to the left side, you get u equal to tan h of lambda u, right? So I want to know the roots of this. That I will split into two curves. Y equal to u is one curve, and y equal to tan h of lambda u is another curve. And look at intersections of these two things. So now graphically you can see very clearly what the solutions will be. If lambda is greater than 1, the tan h curve will intersect the straight line at 3 points. And you can easily see that the difference of these two will look something like this. Right, your u dot as a function of u will look something like this. Therefore, if u is here, it will increase, so it will go like this. If u is here, it's negative, so it will decrease, come like this. So this is a stable point. Similarly, by similar arguments, you can show that this is a stable point, and therefore the central point origin, which is unstable. So for this neuron, it will have two stable states. One is at close to +1, another is close to -1. So I'll call this v plus and v minus. And origin itself is unstable or metastable. But if lambda is less than 1, right, we have tan h function will look like this. There's only one intersection point that is stable, so origin is stable. So what is interesting is in this continuous Hopfield network, right, this is something that we didn't have in the discrete Hopfield network. In the continuous Hopfield network, if I take lambda greater than 1, you'll have lots of stable states. But with the same weight network, right, weight matrix, if I make lambda a sufficiently small number, right, then origin alone will be the stable point, and you won't have any stable points. All stable points will suddenly disappear, which is very interesting about continuous Hopfield network. Okay, so and you can also show that the stationary point is stable. Okay, we'll skip all this. We have just used applied simple argument to show that these 2 points are stable. Okay, same thing you can do by calculating second derivative and showing that the 2 side points are stable. Now, if you take 2 neurons like this, right, then you can couple them by 4 coupling coefficients, W11, W12, W21, W22. And if you kind of store a pattern like 1 minus 1, the weight matrix will be 1 minus 1 minus 1, 1. Because here also, although the equations look slightly different, the storage will exist exactly the same. So here also you have storage is by Hep's rule. So Hep's rule, right, for pattern storage, which is given by this, right? So if if I store this kind of a state, s equal to 1 minus 1, you get this weight matrix. So then what will happen is it will have two stable states. One is at 1 and minus 1, or another is at minus 1 1. The origin then becomes a saddle node, not an unstable node. It becomes a saddle node. Right. So now, we have looked at so far two Hopfield variations of Hopfield model, the discrete and the continuous. Right. And in the original Hopfield model, the discrete one, the neural activity evolves through time. The weights are collected in one shot. But the problem is neural activity evolving through time is okay. Biologically, it is okay. But calculating weights in one shot is biologically not okay, because you never store information like that. I mean, you kind of get exposed to it, and there's a time involved. You don't calculate weights in one shot. I mean, you cannot just program your connections in the brain to be equal to something in 1 second. There is an exposure time, and then slowly the connections evolve, and you store information. So it will be biologically more plausible if weights can be trained over time, just like you train weights of an MLP. It will be nice to train information over time, right? Train the weights over time. So therefore, it will be nice to have a variation of the Hopfield network where the weights are also trained gradually through time, just like the weights of an MLP. So how do we do that? For that, the people have proposed a extended model of even the continuous Hopfield network, where you have two sets of dynamical equations. One to describe the activation dynamics, which is what this is called. That is the VI of the neuron. The state is the activation of the neuron. How does that vary through time? There's activation dynamics. And that is given by this equation, which we've already seen. In addition, now we also introduce a separate weight dynamics, where I describe the weight change by differential equation. So earlier, weights didn't have any dynamics. Wij is equal to SI where SI is a stored pattern. This is a Hep's rule. Okay, here there is no dynamics. Whereas here now we're talking about dynamics. We are saying that dWij by dt is equal to minus Wij plus some VIVJ. VIVJ is the network state itself, the neuron state of Vi and Vj. One more thing is, you see that there are the time constants tau A and tau W. Tau A represents a activation time constant, tau W is a weight time constant. And note that activations are thought to be changing rapidly, more rapidly compared to the weights. Weights are thought to be varying slowly. Okay, so now here also people have proposed a kind of an extended energy function, where up to this point it's like the energy function of the continuous Hopfield network, right? The coupling terms, then the G inverse V, and then the I with the external input. In addition, we have one more term, which is sum of all the weight squares, Wij square. Because if you take this as a Lyapunov expression, right, you can derive both these equations from this. Okay, so which is fine. And you can see that when the weights stabilize, right, dWij by dt is equal to 0, you get this Wij will be equal to VIVJ, which is similar to Hep's rule. It is actually deceptively similar, but not quite if you think about it closely. Because in the Hep's rule, the weight is calculated based on the external input, not based on the neuron state itself. Whereas here, what we get when you set this equation to 0, dWij by dt is equal to 0, you get Wij is equal to VIVJ, which is the state of the neuron. So the state of the neuron and external input are quite different. Let us see what the difference is. Let's focus only on two neurons, ith neuron and the jth neuron. So the state of the ith neuron is Va, state of the jth neuron is Vj. And the two are connected by a synapse of strength Wij. So right now, So since we are not calculating the weights in one shot, we'll have some random initial weights, and then we have to adjust them, adapt them slowly so that they become equal to something that we desire. So what we desire from Hebbian rule is Wij is equal to Sij. This is what we want. So we desire this. Okay, but what these equations are giving us is Wij is equal to ViVj, not Sij. So therefore, if you want to get to this point from this point, we need to make sure that Vi and Vj are respectively equal to Si and Sj. Then we are done. So how do you make it equal to Si and Sj? So how do you make Vi equal to Si? So basically give Si as input to Vi, just right like an external, because there's a provision in the continuous Hopfield network to give an external input. So we give Si as external input, right? So that Vi will go to Si. Okay, if that happens, then Vi, right, Vi and Vj together can adjust Wij, and we are done. Right, then Wij will go towards SISJ. So this we can achieve if only we can make right Si influence Vi and Vi tend to Si. So how do you do that? So basically, what is happening here is the neural states activations Vi and Vj are able to directly influence the weights, right, through Hebbian learning. And like I said, there is biological evidence for that kind of a thing. Now we need to make sure that the external input will now control the neural state, which is reasonable because I cannot use external input to directly access synapses and control them. My external input will produce some activations in the brain. So if I'm looking at a picture, that will produce activation in visual cortex. If I'm touching something, it will produce activation in subsensory cortex. The external stimulus will basically produce some brain activation. The activations in turn will have some effect on the synapses and adjust them. This is a reasonable thing to expect. So what we need is external input I should control V, and V's then will control W's and store information. So I'll present my external the stored pattern, the pattern I want to store S, in the form of external input I, which in turn will adjust V. So how do we do that? Okay, I take my external input Si, inside my input I'm trying to store Si, and give it as external input II, and only thing is I have some coefficient A. Okay, so now I'm using some coefficients A, so that I can control the relative magnitudes of this internal inputs. So each neuron will get inputs from other neurons, which is given by the summation sigma Wij Vj. It will also get inputs from the external input. So to show it pictorially, the neuron state is Vi. Each neuron gets inputs from neighboring neurons within the brain or within the network. It also gets input from the external node. So we need to distinguish these two. This summation of n terms represents the lateral input coming from other neurons. This term represents the external input coming from outside. So I'm introducing two new coefficients, B and A, just to distinguish these two terms, and also with using these two coefficients, I can control the relative magnitudes of this internal inputs and the external inputs, if I want to. Similarly, I introduce another coefficient C here. C here is not a function; it's just a coefficient. It's a product, right? And if I make C equal to 0, weight update will stop. Weights won't change anymore. If C is a positive high number, then weights will change. Okay, so I'll make use of these three coefficients: B, C, A, B, and C. So now, if in a network like this, right? So even in the case of the continuous or a discrete Hopfield network, there are two different stages. There is a storage step and the retrieval step. In the storage step, I use Hebb's rule to just store the pattern S into weights in one shot, and then I freeze the weights. After that, I retrieve it gradually. And how do I retrieve it? I give some random input as initial condition, let the network evolve, and then retrieve this final state. So here also, to distinguish between the two states, the two states of operation of the network, the storage and retrieval, I'll play with these three coefficients A, B, and C to distinguish between these two states. How do we do that? So Wij will be will go to Vi Vj according to equation 2. We know that, right, according to this, right, and equation 4. And but what we want is SISJ, which is we should go to SISJ as we decide. So S will be written into V, and V will then write itself into onto the weights. So for that to happen, right, so for my S to simply, for my S, which is here given in the form of a I, for this to imprint itself completely on Vi, right, my Vi should be equal to AI. That's what I want. For that to happen, the effect of this term should become insignificant. Ideally, should become negligible. So a given neuron is listening to the external input and also this to all these fellows from neighbors. So during storage, I want only the external input to be heard. I don't want all this noise from other neurons. Right? I want to really cut it out. Okay. So how will it happen? That will happen by making A a large number and B a small number, or ideally 0. So A is a large number, B is ideally 0. When I do that, the equation will become just this. This whole term is gone. So tau dui by dt is equal to minus vi plus ASI is my external input I. Okay, so then what will happen at convergence, ui, this will become 0 left side, ui is equal to ASI, and A is a positive number, and vi is equal to tan h of lambda ui, which is this. So you see that vi is equal to Si, right? So which is nice. That's what I want. So for me to store information, I want A to be a large number, B to be a small number. Then Si will simply write itself onto Vi's. But whereas for so then what happens is, this kind of Vi, if I apply to the weight training, so weight training is given by dWij by dt is equal to minus Wij plus Vi Vj. Right, at convergence, you will have the left side is 0, so you will have Wij is equal to Vi Vj. But we have seen that Vi has gone to Si, so it will be equal to SISJ. Okay, so how do we achieve? So once you have that, recall is straightforward. During recall, I don't want any weight change. So Wij, delta Wij will be 0, no change in weights. So it will just run and retrieve the weights. So basically, we need to divide the operational network into two separate stages, storage and retrieval stages. During storage dynamics, A must be a large number, B must be a small number, so that the external input will completely write itself. Because there might be already some random weights, right? That will influence the output of the current neuron. We don't want that. So I'll set B to 0, set A to a high value, C is also a high value, so that the external input will write itself onto V, and then that will get written onto the weights. Whereas for retrieval, I don't want weights to change, so C will be 0. A will just be a small positive number. B must be a large positive number because now the information is already stored in the weights, right? And A should not be a very large number because the external input now will have errors. It will be an incomplete pattern which I'll be presenting for retrieval. So if I give A large, then you're giving too much importance to a wrong pattern. The pattern should be just sufficiently strong enough so that it'll initialize the states of the neurons reasonably well. Now B should be large enough so that because the perfect information is already stored in the weights, it's all that. So B should be large enough because B is the one that's amplifying the weights. So it should be large enough so that it will retrieve the correct pattern. So you see that the two states are very well defined, very well segregated. I can conceive of that if I want to make this network work, I can only do it by operating it into two separate regimes, right? Or stages. In the storage stage, I want to have a high A, low B, and high C. In the retrieval stage, I want to have a low A, high B, and 0 C, or low C, whatever. Right? So this is the kind of thing I need for this network to work. Now, what is interesting is hippocampus seems to have all these features, seems to behave like this, right? So let us quickly look at that and little bit. I'll now quickly talk about some basic properties of hippocampus. The next class we'll combine these two, whatever we say about if in biological terms about hippocampus and all this mathematical stuff we just discussed until now. We'll combine these two in the next class and try to present a theory of hippocampus. So this is from a book called Gateway to Memory by Gluck and Myers. I'll give the reference towards the end of the talk. So hippocampus is called the scratchpad of memory, in the sense, when you want to store something, you can temporarily you just write it on a scratchpad, and then that you will make a fair copy in a bigger notebook later. So hippocampus is like that scratchpad. A lot of our knowledge of hippocampus came from this patient called Henry Molaison, generally referred to HM. I think he died recently, so a lot of so the name was revealed some time ago, and now we know who is HM. Otherwise, literature for a long time they were maintaining the confidentiality of this, the privacy of this person. They should just refer to him as HM. So that is HM. He had some epilepsy problem. So for a long time, the cure for a more intractable epilepsy is just to surgically remove hippocampus, because usually hippocampus is a source of its epileptic focus, the source of epileptic activity. So whenever they find that, people should just remove hippocampus. So initially they didn't know about all these functions of hippocampus, so they thought it's okay to remove hippocampus. So when they actually removed it, right, his epileptic fits as attacks stopped, but then they found that this person had began to have serious memory problems, right, or some memory loss, which is called amnesia. So this patient started showing two kinds of amnesias. One is something called retrograde amnesia. It is the inability to recall old memories. That is, this patient had poor memory of events that happened immediately before surgery, but he had memories of his, from long ago, his childhood and things like that. But he had trouble memorizing new information or storing new memories, right? So to show that pictorially, so this was where the lesion was, right, and this is where surgery has taken place, and he could not remember things just before the surgery. He could remember things well before the surgery, but also everybody has a problem with remembering memories from very early childhood, right, up to about a year or so. You won't remember anything. It's a very standard problem. Everybody has that. So that is always there. But otherwise, because of the lesion, this guy could not remember information from just before the lesion. And so that is retrograde amnesia. But anterograde amnesia means after the lesion, you cannot remember anything. You have memories of the pre-lesion period in your life, but after lesion, you don't remember anything. So HM had both. Okay, so both anterograde and retrograde amnesia. I was talking about LTP, right? The LTP experiments where the schematic shows how it works. So initially, before stimulation, if I give a single action potential, right, to the presynaptic side, the postsynaptic side will have a PSP which looks something like this. Then during stimulation, I give high frequency input on the presynaptic side and depolarizing input on the postsynaptic side. Then I do it for a few minutes, 10 minutes or so. Then after that, you probe the synapse with a single action potential, you get a much larger PSP than before. So this is LTP. Similarly, you also have LTD where you activate presynaptic side but deactivate postsynaptic side, then you'll have a depression of the synapse. So this is thought to be like a basis of memory at the cellular level, right? What's the connection between Hopfield network and the hippocampus? So what I'll do, let me stop here, right? So let us stop here, and I'll get into the details of hippocampus in the next class.